Good morning, everybody, and welcome to day 2 of this year's conference. Yesterday was Hacktivity Now. Today is Hacktivity Next. There's only one schedule change. So far, it's the sessions before and after lunch. So before lunch will be Paul Coggin at 12:25. After lunch at 2 o'clock will be Zoltan Balázs. That's the only change. There are 1 or 2 places become available in the workshop since yesterday, so if you do wish to participate in the workshop, just pop up, and if there's space, you'll be allowed. It's a maximum of 20, but there are a couple of spaces available. There's still the opportunity to challenge yourselves on the 3 sponsors, 3 main sponsors competitions, Deloitte, ThyssenKrupp and Bosch, so there's still the opportunity to give yourself a challenge and win a prize. So without further ado, to start things this morning, I'll hand you over to András Kabai and László Tóth. Welcome, gentlemen.
Thank you. Okay, welcome everybody. I also would like to say hello or welcome to the viewers on the stream. In the next 40-45 minutes, we are going to talk about our experiences that we collected in the last 7 years during automotive penetration testing projects. Who we are? My name is László. I have more than 20 years experience in cyber, especially in the penetration testing, and one of my responsibilities at the workplace to build our automotive cyber lab and knowledge.
Hello everyone, I'm András Kabai, working together with László, also have strong background in penetration testing and IT security, and I'm working on automotive cyber and penetration testing projects since 2015. I'm also responsible for car hacking and hardware hacking services in our team, and build several stuff for our clients, including car hacking training environments that we also provide for OEMs and T1s, for example.
Okay, what we are going to talk about. The presentation will have 3 main sections. The first section will talk about why we should focus on the automotive cyber topics. The next one will talk about why we have to deal, or how we can deal with this complexity that we will describe in the first section. And the last one, we brought you some examples. Of course, we cannot show you the examples from our clients, but we built some interesting stuff for you. So the first part, the why. So I'm old enough to know that we were quite happy when at the beginning we had just a radio and the CD player in our cars, and we were quite happy if it was capable to play an MP3 CD. And then the small screen appeared in the car, and it had a GPS service, and the number of ECUs in the vehicle was quite low. The ECUs meaning the small number of computers inside the vehicle, meaning the embedded systems. But lots of change happened in the last 10 years. The mobile phone appeared, everybody wanted to connect the mobile phone to the car, use it, charge it, so USB, Bluetooth appeared there. Then if the mobile phone is so useful inside the vehicle, why we do not install a SIM card in the vehicle itself, so have its own mobile connection. If it has its own mobile connection, why we don't connect to the internet already? And if it has an internet, why we don't share this internet with the passengers? We tested car who has 3 different wireless networks in it. And if we have the internet connection or a GSM connection or 3G, 4G, why we don't connect to a backend system and start collecting data? And if we have a backend system, why we don't allow the owners of the vehicle to use the same backend system with a mobile application or a web application? And there were another trends, the number of ECUs, the small embedded system inside the vehicle, increased dramatically. The first car we tested 7 years ago had 50 ECUs in it. But, of course, the development didn't stop here. Everybody talks about autonomous driving. system. So we need new sensors and cameras. I'm not opening the debate here. Someone says new sensors, someone says lots of cameras. The main message here, you need more components inside the vehicle. Moreover, there are new protocols when they are saying, okay, the autonomous things would be much better if the vehicle can talk to the infrastructure, can talk to another vehicle, as a summary, vehicle to every single vehicle to X. It's a very complex PKI-based protocol. Some also says you need a high precision map to be able to perform the autonomous driving, so another backend solution, and I'm not talking about the Google Maps, where the car should constantly update what he sees or what it sees, and also constantly request information what he can or it can expect. So if we are talking about the autonomous driving, then the car has to make decisions. So we need a powerful computer that's able to run machine learning models. But if we have autonomous driving, we have to entertain not just the passengers, but the drivers also, and we need more powerful computers to entertain. So basically from this, we are reaching this level. So maybe the Night Rider won't be a sci-fi anymore. But let's translate this to, or let's bring this down to the ground with this simple diagram. So basically what we are seeing is that we have many, many backend solutions, clouds, and so on. We had a vehicle, he has its own interfaces with wireless. We had application like mobile application, web application. So basically, everything that we did in the last 15 years just increased the attack surface of the vehicle. And all of the components can be targeted. Besides that, the interior of the vehicle system complexity just increased. You see a very rudimentary example on the screen. The first car we tested had 18 different buses that connected the ECUs together, that 50, 60 ECUs. And that bus system can be different. It can be CAN bus, Automotive Ethernet, FlexRay, MOS, and Lean. And one of the main aims of the attackers is to change the vehicle behavior. And to be able to change the vehicle behavior, they have to understand what's happening inside the vehicle. Therefore, we have to protect that one complex system also. And in the future, they are talking about, or there are already cars out there, talking about software-defined vehicles. And just it's meaning lots of things, and it's a wide topic. The only things that I'm showing you just as an interesting stuff, the embedded system getting more and more powerful. So the ECU is getting more and more powerful. So what you saw in the IT world, that the virtualization appeared, and once hardware started to support multiple roles, this is happening inside your cars. So basically the conclusion of this section is that the new technologies are there, they connect to our car, even they will drive our cars, and the vehicle now is part of a complex ecosystem, and the vehicle itself is quite complex, and this new ecosystem is vulnerable to the same cyber risk as any other IT network. And of course, the automotive industry recognized this quite early and investing heavily. And how early it was, all of these research results or presentations that I'm showing on the slides right now is from 6 years ago, so 2015 and 2016. And I choose these because they represent quite well all of the components of the connected vehicle ecosystem can be target of an attack. Of course, the groundbreaking one was the Charlie Miller and Chris Walaszek, and I'm considering it is not just because they were first, but basically their research paper is just a map how you should set up your automotive penetration testing methodology. Only one thing missed from that paper is the backend system, but they went after the Wi-Fi, the GSM network, they found a vulnerability in the infotainment. With hardware hacking and reverse engineering, they learned how to bypass CAN filtering, You will learn later what it is. And also, with reverse engineering techniques, they learn what they should send to the car ECUs to change the behavior of the vehicle. So the whole picture. The next one, the semi-cam car, is a very good example that there weren't any vulnerabilities in the vehicle itself, but the mobile application that did some control on the vehicle didn't check the server certificate. So it was easy to man in the middle it. The next one is a Nissan Leaf case. It's not about the car as well, but the backend system and the application. Basically, it authenticated the request from the mobile application that controlled the car just with the VIN number and the vehicle identification number, which can be considered public because in some cases it can be brute force, or you can walk up a car outside and check on the windshield. The next one, they did many things, but what I liked and shows very well, you have to focus on the cyber security for the vehicle, whole life cycle of the vehicle, which meaning not just in the design phase and until SOP we start the production, but until it is on the road. Because what they did is just dump the infotainment system of an older car, and they find a URL in it. And the domain part of the URL wasn't registered anymore, so they registered it. And cars started to talk to the system. And the last one is a very simple one. In this case, there weren't any backend system. It was the mobile phone and the car, but the Wi-Fi network that the car provided has a weak Wi-Fi password because the generation of the password wasn't random enough. So they were able to crack it, WPA2, quite common technique, and then talk to the car, and the mobile application security of that protocol security relied on the Wi-Fi security. So they were able to switch off the alarm system. So as a summary of this slide, all of these things shows very well every component of the connected ecosystem can be a target. And the automotive industry knows very well. This research just published 2015 and 2016. And invested heavily. Moreover, the regulators also realized there may be a problem arriving here. So there are regulations out there and there are standards out there. And this is not the conference to go deep dive into this. The main messages are the following. All of the standards says you have to deal with you need a cybersecurity management system that has to deal with the cybersecurity of the car for the whole life cycle. So not until start of production, but after that as well. And they are already in effect in some countries, in the UNEC countries, which means if somebody released a new model in 22 July or after 22 July, they should able to prove they have this CSMS and the car developed that way, because they cannot homologate it in any other way. From 2024, they have to do this in a term, they have to do this for all the cars that they're selling currently. And this leads us to another topic. So in the last 7 years, we experienced a considerable improvement of the new vehicle models or new cars on the street, which means, for example, the entry level are considerably increased. The gateway module that separates different buses is not just translates between the different bus types, but also have security functions like filtering CAN messages. The CAN-FD or Automotive Ethernet provide enough bandwidth to apply some security measures on the communication. Simply connecting to the OBB2 by a technician and perform a privileged actions like replacing a firmware, it's not enough anymore. It may require a strong authentication, including an online system. And the firmware is getting digitally signed and encrypted. So our conclusion is that the penetration testing, researching, or car hacking is getting more and more complicated. It's not just simple plugging in the ODB2 port and you are good. So how we can deal with this complexity and this new increased security? And now I'm going to state the obvious. So basically, you need a lab, you need a team, and you need a methodology. Regarding the team, you saw that the connected vehicle ecosystem contains everything that a modern IoT system can contain. And in the penetration testing industry, we already specialized. So somebody good at web hacking, mobile hacking, somebody good at the hardware hacking, somebody good at the red teaming. So you need a diverse team to be able to handle this complexity. Regarding the lab environment, because you need to do hardware hacking to understand how the car works, then you need special devices to conduct this hardware hacking. Moreover, you need it's not just ARM or Intel. You can find many other special MCUs or CPUs that you should be able to handle. The car, there are especially a bus system, as we mentioned, which means you need FlexRay interface, automotive interface, CAN interface. CAN is easy, the other two is getting a little bit expensive. The automotive industry had serious, long time on the market software stacks to develop their cars. And this software stack, and they are using these software stacks to simulation of the car, of the ECU's behavior. And as a pen tester, you may need it, because if you just receive an ECU, most of the cases the ECU needs the other ECUs to behave properly, meaning receiving the right CAN messages or right messages on the automotive Ethernet and its interfaces, and you have to simulate that. This is called REST-bus simulation. And of course, I already mentioned to you that the special debug equipment, like this Lauterbach stuff, to be able to connect the special ECUs and debug at the special MCU CPUs and debug at that level. The next and the last thing is the methodology that you need. What the cyber industry does when he sees a complexity, and it's hard to decide what to test. So if you meet a car that has 50, 60 ECUs, hell of a lot of functionalities, what to test or what to secure. Then they are doing this threat and risk assessment things that basically who is your attackers, what they want to do, what they want to reach, what kind of functionalities you have, what kind of attack surface you have, and combine the both, and you will receive a result that you can end up in a test plan. But as the regulations and the standard says, you have to do this at the beginning of the development to know what kind of security controls, security goals you should have. As a pen tester, this information is really good, because then you can formulate a flexible test plan, what you should go after. And when you have to test a vehicle before start of production, this is crucial information to be able to use your resources effectively. Of course, sometimes you don't have these thorough results, so it's better if you are prepared your own that is focused on the pen testing task. What are the typical requests that we receive? Test the whole vehicle, test the functionality of the vehicle, or test just one ECU or one component of the vehicle. And depending on the scope and the resources, you will do that typical test types, from hardware hacking until the backend. And just only one comment from me that you can see the sentence on the slide. The penetration testing should be integrated in the V model. I'm not explaining what is the V model right now, but basically what it means, if you start the penetration testing activities early, meaning there is a CPU, there is an ECU ready, or there is a functionality ready, and you do pen testing activities, then you have to do less testing activities when the car is ready, and before starts the production, you do the final penetration testing. So you basically, in this complex system setup, you have to do or build up a hierarchy of testing activities. And now we're going to the how, and I'm passing over to András.
Okay, so to provide you some examples how these testing activities are ending up in methodologies, we provided you some examples. So for example, starting with bus and interface testing, that is the most common testing activity against the car. And take CAN bus, the most important communication system since 20 years in the cars. What can you do with CAN bus testing? The common knowledge is that you go to the car with a small OBD plug it inside the car. It has Bluetooth connection or Wi-Fi connection. This ELM chipset-based plugs can be purchased from AliExpress for $2, and you're ready to go and ready to hack your cars. Maybe it is good for reading out diagnostic codes or maybe to clear out error codes, but in fact, it is not sufficient and good enough for perform any kind of meaningful car hacking. The OBD port and access to the in-vehicle networks through OBD port was possible without or with very few limitations in earlier models where the gateway did not make proper filtering. So there should not be a case right nowadays where from an OBD port, from an external communication interface, you have any kind of possibility to have influence, for example, on safety critical buses or components. So it is filtered, it is blocking you, you cannot send inside a message from external interface, and you won't see any kind of communication that is actually happening in sensitive bus systems. But still, what you can do with it. In case of penetration testing, we typically start backwards, so meaning with full access and direct access to the ECU, to the given bus, to the given component. So we go there, we tap there, and perform the testing activities there. And if we find anything at this stage or at this point, then we step backwards and check from where this can be exploited from somewhere else, from a different bus system, through another components, or from different entry points. So in case of CAN bus system, it is no longer just, capturing something, replaying and enjoying the results, because that was happening before. Nowadays, sensitive communication is protected. It is, there is a SecOC, Secure Onboard Communications, message authenticity and integrity is protected, which is, in case of standard CAN 2.8, is quite limited due to the limited 8 bytes that you can use in messages, but the industry has already introduced CAN FD, for example, which much bigger payload size, where feasible protection, HMAX can be used, for example, on the messages. Still, the same applies to FlexRay and especially for Automotive Ethernet. So in case of these bus testing level activities, we definitely go against sensitive features and functionalities against the ECU and diagnostic, because this is one of the most important things that could target it by an attacker. Diagnostic may provide access to the internals, extracting of RAM contents, flash contents, or may provide ability to attacker to manipulate the ECU somewhere. So bypassing security checks, authentication controls, and stuff like these are all in scope of this type of testing activities. As due to the complexity and the increasing amount of bandwidth needed by the functionalities in the car, Automotive Ethernet appeared and introduced to the vehicles. This is, on one side, a very great improvement to the whole infrastructure and to the possibilities, and they already made thousands of well-known technologies available at the cars. And so you can easily find the HTTP service or SSH in the car that uses, for example, Automotive Ethernet. But on the other hand, it also introduced the same vulnerabilities that the traditional IT systems has. So you can now use a standard vulnerability scanner that will map your components, scan the IP addresses, scan the ports, and look for traditional vulnerabilities, and use traditional IT security knowledge to target the car. Of course, there are automotive-specific protocols, solutions that needs to be tested and evaluated, and this is all part of the security testing activities here. Hardware hacking on component level is always a very important part of the penetration testing, because you will see it later, different approaches, different testing activities against the same target may provide you some important findings that can use later in a different stage of the testing activities. In case of circuit level assessment and the hardware hacking, we always go after the given hardware. We check what kind of chip is used, what kind of security features are available, whether sensitive data is stored inside or outside of the microcontroller, trying to extract sensitive data, access to diagnostic and debug interfaces, low-level communication, inspection between different components, talking about about chip-to-chip communication, interfaces, and so on are all in scope. And this is in parallel with the firmware level assessment, which can happen if you are able to extract the firmware, for example, from the target itself or from a firmware update process during the diagnostic and flashing process, or you received it for the penetration testing. And firmware level assessment could and may help you by identifying sensitive features relevant from security perspective, and help you identifying those sweet points that you need to investigate deeper. So for example, check how the secure boot is implemented, how key validation is performed, or how sensitive features are protected inside of the ECU. These are working in hand. And just to make you more comfortable with this testing approach, we provide you some examples, starting with connected testing approach against an ECU. This is one of my favorite examples because it shows you very well how different testing activities could help each other. So we had a target ECU that uses a high-end, state-of-the-art microcontroller with plenty of security features included, and we started with hardware hacking. So open the box, go down, investigate it with microscope, tap for the right points with the right debuggers, investigated the communication with logic analyzers between components and so on, but there was nothing serious there. So after a certain amount of time and with the finished test cases, we decided that we had to stop there. So we switched to interface level testing activities where we jumped back to the CAN bus and performed the bus testing and interface level testing activities there. It turned out that there was a service there that was vulnerable because of a weak implementation, and this diagnostic and calibration protocol made it possible to access those sensitive memory areas that was not supposed to be accessible by the externals. So especially not without authentication. And by knowing the memory structure of the target MCU, we know where the sensitive information were stored, for example, for the GTAG lock password. And we simply extracted the sensitive content from the microcontroller through the vulnerable service over the CAN bus. Having access to this sensitive information, it was possible to go back to the hardware investigation, go back to the debugger interface, unlock the microcontroller unit with the GTAG unlock password, and have full control over the microcontroller, the code execution, have direct access to the whole firmware and every key materials used inside of the ECU, meaning secure onboard communication bits, key materials for firmware cryptography and signature validation, and everything that is necessary to compromise the ECU or manipulate it. So this clearly shows how testing from one single perspective and one single entry point is not enough, and one you have to combine different kinds of testing activities. Moving forward with some IP.
Okay. So it's my turn. So András already explained that why the automotive Ethernet appeared inside the vehicles. Basically, it was bandwidth related. Of the audio-video stuff. But also it opened to many other possibilities. And the automotive industry realized they need a protocol where the ECUs can call functions of each other, or one ECU can notify another ECU. And and that's why the SAM-IP was born. Basically, it's an RPC protocol, and it's a service discovery protocol. And the behavior is quite simple, or it seems simple. The ECUs that have functionalities to call or events to send out advertise this. And they are advertising this to the multicast addresses. So if you are already inside the automotive Ethernet and you just sniff, you don't do any man-in-the-middle attack, just sniff, you will receive this advertisement, and you can see what kind of events are there or what kind of functions are there. Basically, you will see numbers like event ID, service ID, and this kind of information. And another issue, if he wants to receive an event from the given ECU, he can just send a subscribe, he will receive a subscribe back, and later, when the event happens, he receive the notification. This is how it looks on the network. Of course, this example that I developed for demonstration purposes, if you see in the car, that can be much, much more. Many, many services and many, many events. That's why it's not easy to find out which are cyber relevant. And the main problem with the SAMIP protocol is that by default, it doesn't contain security. So you have to add the additional cyber security layer yourself, like protect the automotive Ethernet with IPsec. So, but if the attacker is already inside, he can see this kind of packets. As you can see, the service discovery packages just sent out to multicast, and you can subscribe, and you will receive an acknowledge. And an attacker can do the same. It's very simple. And how simple it is, this is a sample Python script that I wrote. It's based on Scapy, a well-known Swiss Army knife packet handling for Python. This code just sends out a subscribe things, basically puts together the SAMIP packets in the right way. The Scapy has the SAMIP module to support this. And you, in the subscribe message, you just have to tell, I would like to receive the events on this IP address and this port. So this is how short this Python script is. And the next Python script just shows, using the same Scapy module, how to sniff on the interface and waiting for the given event. And if you receive the given event, then just start something, do something. And basically, the events there to learn something new happened inside the vehicle, so some actions will happen. And in this case, it's quite, how can I say that, basic, because we're just downloading a file from the server for the demonstration purposes. I'm not telling anymore. And now we are switching to the firmware case, or the reverse engineering stuff. The main problem with the automotive reverse engineering is twofold. First, you can easily find a very exotic CPU that is not in the normal IT world or IoT world, and a binary firmware, there is no operating system for it. So you have to learn how to reverse that. The second thing is that you will find quite a normal ECU with a normal CPU with a normal operating system, but with a highly complex software stack above this operating system. And you have to learn how to find out what to test. And what you can do, for example, if you find an operating system with a heavy software stack, you would like to learn which processes are interesting, which processes has some cyber functionality or network function, listening and CAN bus network, or the typical hardware interfaces like serial, SPI, I2C. You want to learn which one is used, cryptography, how the startup works, how you can change the startup functions, and then you have to make the decision whether focused or a little bit general reverse engineering applied. And I'm going to show you two examples for this. The first one I chose because just have the opportunity to talk about the automotive grade Linux. It's an alliance, many OEMs, meaning car producers and tier ones that create ECUs to the car producers, supports this alliance. They may aim to create a software stack, APIs, interfaces that makes the Linux usable inside the vehicle, and not just the infotainment, but for safety critical systems. Time to time, they're releasing demos On your screen, you can see a screenshot from the infotainment demo, but also they're doing demo for the instrument cluster. And just telling you, they already started to using container technology in there. So the complexity from the IT system starts arriving inside our vehicles. So this is a very simple sample. I wanted to learn how I can find out which process in this AGL demo system uses the CAN bus. And in the Linux system, it can be easy because there is the scikit-can in the Linux kernel, which is quite stable and usable. And you just need a tool that tells you, when you list the open socket and the system, which one is CAN row. So on the screen, you can see it was the process 331. There is another Python-based process, but it's a long story, 331. And then I'm just applying the well-known trace tool, go after the send to, and I'm starting to see the CAN messages. If you look at the another side of the slide, you can see which kind of CAN message was sent out by that process, and you can see the same CAN messages in the trace output. x64, x64. Of course, in the real life was totally, it can be totally different. I had a case when huge software stack and there were no scikit-can, but CAN message leave the ECU. And it required lots of debugging and reverse engineering just to find out they're using a special serial line, a special devices, and the CAN message was just packaged into another protocol, to the serial line, and it somehow ended up in the CAN bus. But at the end of the day, we were able to write a Python script that simulates this. My last example is sometimes in this tutor IoT world, you have to do general things to just learn what to do with the firmware. And in the custom developed, from the custom developed libraries, you find a custom library that does some interesting things. The next thing you would ask, which other binary uses that library? It's quite easy to find out, to be honest, on a Linux system. You can check, for example, the open files and which process opened that library. But doing this for many, it gets time consuming. So that's why what I did is developed a very small, just a couple of hundreds line Python script that basically goes through the binaries, goes through the libraries, and builds a graph. And the graph tells this binary called this library, and this library called this library, this library called this library, and also collects which function were imported into which libraries. And the screen, and why graph? Because there are lots of easy-to-use tools, even graphical tools, that you can use to search a graph or analyze it. And the screen, you can see a screenshot of this. This is from our training, Automotive Penn test training. We developed that tool that listened on the serial port and authenticated the user on the serial port. And this tool is the diagram tool, and you can see which kind of libraries it used. It's a simple case. It used the libcrypto library, which is part of the OpenSSL. The tool itself that I used is the Cytoscape. I don't know how to pronounce it. But basically just searching for functions, it shows very well the diagram interacts with libcrypto and using this function. Of course, in a real-world scenario, where I just developed this, you will have much more results, and you can really start to work how to reverse engineer or learn which one is important and which one is not. And then you can use your GIDRA if the given CPU is supported to do the reverse engineering. Of course, I'm not going to explain the reverse engineering process right now, but whenever you have the function and you have the function that called and you have the binary, from that point on it's easy. And you ending, yeah, I draw this ASCII art. But anyway, at the end, you just can find out the authentication happened from this file. And it was an MD5 hash, and you can crack it. But this is just an example from our training. But in the real world scenario, this method that I just showed you helped me find a lot of vulnerabilities and weak crypto usage and keys and crypto keys in files unprotected and so on and so on. So the summary. The vehicles, complex, currently under heavy change. So maybe there will be fewer number of ECUs because of the electrification, but that given ECUs will be much more complex and does many, many things. The ecosystem around the car just getting more and more complicated because the automotive industry, from business perspective, would like to serve you with many, many services that you are paying for. That's why we should handle the whole ecosystem. And that's why the automotive penetration testing right now is a team effort. You need wide variety of expertise, and you need a well-equipped lab to perform it well. But it should not stop you. It still can be fun for researchers and hobbyists. And I just put here some pictures to prove that. For example, this 2 picture is from András' car. Because in our training, we use the instrument cluster, and this instrument cluster, we have to learn how the CAN messages are working. And as you can see, it was just dismantled, and we just connected to the CAN bus. Not an ODB2, of course, so some dismantling required. The another fun fact that I wanted to share with you, this is a very expensive CAN bus device. Hell of a lot of money. This is USB 10. How much? 20?
About $20.
Yeah, $20. And most of the case, even in professional cases that we are doing, it's enough. So maybe you don't need this. And of course, there are lots of things where you can just learn, use toolset, learn, like automotive grade Linux, how these new shiny cars are working. And of course, you can start to build your own environment and practice. So thank you very much. That was that we wanted to share, and I hope you will enjoy the rest of the activity as well.
Thank you to László and András. I think we have time for a quick question or two, if we have any. Oh, here we go.
Stand up.
Hi, thanks for the great talk. So one of the main takeaways for me was that the whole evolving industry is still a wild west, like lots of complex new technology and all. My question is, as a cryptographer, is that whether you encountered architectural, decisional problems, so not like implementation, hardware level issues in cryptography, because in your line of work, because last time I heard Bosch had some super niche, non-standardized way of doing PKI and firmware signing, because turns out that PKI hardware is too expensive for a car. Is that still the case in your experience?
My microphone still working, you can hear me?
Yep.
Just look at the SecOC. SecOC is a standard, and what it does, because in the CAN bus you have just 8 bytes, in CANFD you have 64 bytes, but it generates the message authentication code with the right algorithm, but then it just cut the hash. I think you know very well the consequences. Okay. And the another thing, you know, that you are right. So the cars in the past doesn't have the necessary processing power to handle cryptography. But nowadays, the high-end CPUs and MCUs, they already started to get the HSM, and they are getting more and more powerful, so sooner or later this will be solved. Of course, the cryptography is hard, so it won't be solved, but they will try. And it will be good.
Okay, thanks.
Yeah.
Thank you for the question. Again, László, András, thank you both very much.
Thank you.